Okay, let's get started. So today Chun, our PhD Chun, is going to introduce his brief work regarding Mask Generative Transformers. So let's get started.
Okay. Hello everyone. Welcome to today's seminar. Today I would like to introduce and present some of my research for the topic of generative AI models with the Mask Generative Transformers. This is just introduced by recently is a conference in CBPR, and this technique can so develop parallel with the model, and it shows some many advantages in the model training flexibility and its remarkable performance. Let's get started. The generative AI model refers to the machine learning model that can generate the new data from some existing data and some learned distribution. For example, the image on the right hand side, we can see this is a totally new data, new image generated by the Stable-Diffusion model. That for text to image. To pass with research, this is only the input to the model and output in the image. Generative AI has been used in many applications. That is very important in the life, and it go to the human brain, image generation, speech and music generation. With many applications we see recently. So in the history of generative AI, we have many models developed with first from 2013 on with the VAE and Generative Adversarial Network on the 2013. It is about 10 years ago. This kind of model is so that it can generate very high quality images. And next, with the advance of the transformer model in the neurons around 5 years ago. After that, attention have been deployed to soon can beat the traditional recurrent neural network. So based on the transformer models of the AI, maybe several versions of the GPT. It stands for generative prediction transformer, and this kind of model so many advantages in the natural language processing. And among 3 years until now, large language model and man-made models with the main backbone in the transformer has so many advantages, and it can have many notable performance on the some applications, and so some image generation models like DALI and Stable-Diffusion and Google Images just this year. So in this seminar, I am focusing on the Mask Generative Transformer. It refers to the new technique, some new technique that is the transformer model. And this transformer has been used to predict in some of the mask data modeling. And this technique has been applied to many other domains in several works, for video, for text to image, sketch to image, and many others. It first appeared on the CBPR 2022, and this approach can outperform many others state-of-the-art, while it is also much faster in the inference. For example, some diffusion-based model stable on image and also the all of these models for text to image, it can so very interesting results. If you have time, you can try the application. We have the online version. So because of the VAEs and GANs, it has been developed long time ago, but they suffer from many crucial issues like most collapse, and it is very hard to train. During training camp, this model it is very unstable. So it motivates the researcher to develop new technique so that it can train more easily and it can perfectly prevent the mode collapse. So there are two solutions that have been emerged recently, including the efficient models and Mask Generative Transformer. So this kind of new technique can generate the very high quality output, and to achieve that, they have to also have some cost. For example, GAN and VAE, they can generate the image just in one shot from the latent space. But for efficient model and Mask Generative Transformer to generate output to get the good enough quality, they have to do the iteratively generation. For example, in an efficient model, normally it requires dozens to thousands steps. LDM is stand for latent diffusion model. This model put on the latent space of the big event, it requires more than 200 steps. So it means that model need to go more than 200 times to get the one output. And the Mask Transformer is also use the multiple sort to generate the output image. And this one normally in the IC they just require less than 20 steps to get the good enough result. Of course, this model generates the output much better than the previous VAE and BQM and GAN model. So in this seminar and my research, now I only focus on the Mask Generative Transformer. So the first paper that is the kind of foundation on this approach is the title is Mask GIT. We call it MAGT, and it comes from some research team from Google. To motivate that work, we first come from one of the paper, big event, city paper on the CPPR 2021. Here is some output generated by the model named BQN. This is high resolution image. You can see it has look very real and it can generate with the high resolution. To generate this kind of input, this kind of output, we first have the input that is the low resolution. For example, it has a part of on the left, for example, 242 a square like this one, and model will try to infer the next frame, and totally they can generate the as many analog as possible, even though they can generate is much more bigger of the design. So this paper they based on the technique of how to regressive model. I think maybe for some people that didn't know or forgot how regressive model work, I can explain a bit. Regressive model it means autoregressive. It means that we predict the output, the future value based on the past data. It means that we can only predict it given some past input. For example, assume we have the input is here. We have first position, the first position. So the model can predict the Poisson as the number 1, and it continue predict 2, 3, and so on. That we call auto-regressive model. So, but the ZCAP approach have several crucial issues. So, first, this approach treats image and a sequence of tokens, and there is the auto-regressive decoding. So this means with the ZCAP sequential image, for example, on this image we have a series. Its lattice space it will be 16 by 16. So it means that this one totally around 256. Here only we have only around 16, but it's just for illustration. But the real reality we have around 16 by 16. This is input. So the model will predict how to regressive around more than 200 steps. So this one for the higher resolution. This one is output is 256 and 256, and this one is the latest space of the image that has the 512 multiplied by 12. So model we have to have many steps. So it generates the output is very slow. So in this paper they propose a mask strategy so that can speed up and generate output with very high quality. And they already demonstrate that this mask model can speed up to more than 60 times compared to equivalent model. Because, so I will present the main idea of this paper, when how to train it and when to use the inference. In the Mask paper, we have 2 stages. So the first stage is tokenization. Tokenization on this stream. It means that given an input image, this state we will try to fit the image to the decoder and take some vector quantization to the discrete. In this latent space, we have the size is 16 by 16. So it means that from the input, given input, we have the size of 256 multiplied by 256. Now our model already compressed 16 times. So now we only use this latent space 16 by 16 so that we can fit to the training decoder to reconstruct image. So the first step of the ZCAP method, we need to train the model so that it can perfectly reconstruct even the input. So after we train successfully the model, this model is going equivalent. First stage, and the second stage, we will have a training. We only training on the latent space of the visual tokens. The visual token is just some number, just an integer number. We have 16 by 16 equal to 256. Train on this sequence and feed into the bidirectional transformer here. So when during training, we just randomly marked some token on the latent space here, and ask the bidirectional transformer to predict the position that we mark out. That is the main idea of this paper. And this is during the inference. Here we compare two methods. The first is the auto-regressive decoding, and the second is the parallel decoding of this paper. So with the previous approach, we try to infer with the auto-regressive. For example, in the first point, first step, we have the every token is masked. We have nothing here. We expect to generate some output that is meaningful on the final. Yeah. But the big event model, we have to predict one by one. In the first step, we predict the first positions. So we have only one output, and gradually t equal to 1, and so on, 0, 0, and so on. So finally, we have to totally 256 times to have the final output, this one. But in this paper, Mask model, because we use a bidirectional transformer and we can predict simultaneously any position. We don't need to wait some output to predict the other. So in the first step, we also mask out everything. We didn't have anything here. So the model try to predict by some schedule, some masking schedules, so that in the next step, the model can predict many positions to get simultaneously in parallel. So totally on this approach, we only require less than 10 steps so that you can model already produce some meaningful and sufficient high quality data. So to compare, we can see the speed of the inference. The left hand side is the auto-regressive decoding of the big event model. It predicts one by one, row by row in auto-regressive manner. So it took many times. And the right hand side, our model can predict many positions together. So during the same time, the right hand side will already predict many outputs that have the real equality, and the left hand side took too many times, and the right hand side chart so that with different resolution. This approach can have many advantages compared to different stuff with the auto-regressive model. So I think this kind of approach will be the future in this field. It is stable, so some comparison with some earlier state of the art. This model, named Mask it can meet many other diffusion model with BBWAN and some band approach, some other. So they measure by FID and insertion score. And another metric, they compare the CAS, classification accuracy score. So they try to generate some class of the image net and try to do the classification on the generated image. And we thought that the system model can generate output class that have much better compared to the previous approach. Here's some other application of this approach. We can use inputting or outputting some stuff for image editing. I think it's so interesting. Based on that technique, some researchers try to extend that technique to other domains. For example, in the text to image.
Sorry, can I have a question on the previous paper? Can you go back to the methodology?
This one?
Yeah, that's one. I want to ask that. So you present that the first stream is for like embed the image into like visual tokens.
Right.
So that's the understandable. But the second stage is really like difficult to understand. Can you explain it a little bit more detail? Here, I would explain that you have some kind of mask tokens,
right.
And then you go inside by bidirectional transformer, and then somehow you try to recover the predicted tokens. Right. So I would like to ask, where is the mask token come from, and where is the predicted tokens come from, and how can we train that using bidirectional transformer?
So this is, for example, here is the visual token, right? Even if we have just visual token here, we have to mask anything, right? So now we just use some randomization to select some position randomly to mask. For example, we will randomly select 1, 16, 20 here. For example, just 3 mask positions. We will have the number, yeah. We have number 1, 10, and 20, for example, there, right? And we just put all of that one to the bidirectional transformer and predict only 3 positions.
Only 3 positions.
Yeah, so that this model can learn the relationship, because the bidirectional transformer is has a self-tension, right? So we can have learn the relationship between each token together.
So bidirectional transformer is a bird line model.
Yeah, that actually it's exactly the
for
first model. It's just
bird
first model. Yes,
bird
exactly.
model. Oh.
So it's just the model from that one, exactly the same model from the language, natural language processing here. But input is just the visual token instead of NLP. Okay.
Okay. So in the next slide we have like the prediction. So the first stream you mentioned about like sequential decoding with autoregressive transformers. So is it like we have the everything in mask?
Yes.
And then it predicts the first pixel and then second pixel and so on.
Yes, right.
And how can it generate various images? So in the beginning we only have like everything masked, right?
Right.
How can the image will be diversified?
Yeah, I think that is good question. So that is seems separate technique. So for this one, they try to add some randomness on the first thing, and during the next step inference, they also add some randomness on here. Yeah.
So it predicts the pixel, and then we add some noise.
Right, add some noise, yeah, some kind.
And then we generate more. So we have no control about the image generated.
Right.
And okay, that's great, cool. And the second line you mentioned that there is some kind of scheduled parallel recording with mask it, but it's a little bit hard to know how it works. So in the first step, we mask everything.
Yes.
We give into the bidirectional transformer,
Yes.
and it will predict like three points.
Yes.
3 points, and then somehow you choose 1 point.
That is just for tuning, right? So in the tuning, we just so in this the first step we can, because in front of this to random. So maybe this step we train we only mask 1. Maybe next step we mask many other. So if we train for many large iteration enough, so it can cover many cases that you have only 1 or 2 or several.
Okay.
So it doesn't mean that in next step we only mask 3 or any number. We totally random.
Okay.
But in the inference, we do the 1 by 1. Not 1 by 1, I mean the first mask everything. But after that, yeah. So it predicts with some mask value, and they propose some confidence score, so that they only pick the token that have the highest confidence score as a mask again. For example, in this step, if the model can predict, it can predict all the tokens, right? Because they only keep maybe the highest one here, highest score. Because we predict the probability, right? So we can always select the highest prob. Yeah, we can keep this one and then mask again and one other, and the next step together. If there's some mask already keep, they will never be masked again.
It's just like we will use that for the final.
Yeah, we will that for
the final image.
Yes.
And then gradually generate more like final image pixels.
Yes, right.
Until it cover like the whole
until final step we have no more mask.
Oh, I see. Cool. So in that way we can reduce the number of steps.
Yes, actually, on this paper they saw that around capacity around less than 10 is enough.
Wow.
If they increase the T, the quality is not better. So I think in the diffusion model, they only in the first stage they divide out 1,000, and later on they develop some new diffusion so they can reduce some around 100, but still very high. But I think it can normally have the sufficient quality.
Do you know what is the size of the image, the generated image?
The size of image. All this paper they added with two resolution, 256 and 512.
512 by 512.
Yeah, yes, right.
Oh, cool. Thank you.
And so, for example, in such if we typically they train on the 256 by 256 pixel, but later on, this model can easily extend because they can really mask this part and use this one to select the right hand side so that from the 256 we can extrapolate to much higher resolution. And in the Soviet, but in the main paper have the very high resolution, which can look very extremely like this one. So this image. For example, here we have only input only this part. Try to imagine this input on input model. 256 by 256 here, and ask the model to predict all other right hand side and left hand side here. And finally we can generate the high resolution. Even though we can also predict on this part and this part, so it can be much faster and we want.
Cool.
Yeah, input only small part like this one. Model can know and predict all other things and look very real. So this is the next application. So they extend to the text to image. So during the training, instead of only image, they add one conditional modality like text here. They embed the text encoder and they concatenate with the visual token and use the cross attention transformer to train together with the sum token of the low resolution and the high resolution. And it's quite straightforward, and the main thing is mark the token and train it together with the other modality like text here, and you can see the output can generate something very meaningful output on the right side here. And on this paper, they only also different with around less than 10 steps that can pull it up for the image. And compared to Stable-Diffusion here, this paper can have the much better score in the image evaluation. I mean, so some people check some picture, and they saw that this picture look real, and they put some wood, and this paper with much better compared to diffusion-based methods. So the second important paper, this is also a spotlight paper on speed up this year. So they explain the image to the new domain of the video. Its main idea of this paper is they try to consider many masking strategies for each task during the training. For example, they propose about 10 tasks. Even the one video with the many frames, they put the encoder, they have the latent space of it, and they try to mask. For example, when we first start, we just keep the first frame and mask all other things. And as a transformer model here, we predict the token that is masked out on this part. That's the main idea. And during training, they just sample some tasks and training many long time with the variation transformer. And by doing this, they can generate the video with a very real and have very high quality based by the activity. The complete video distance. Yeah, so we can see this model compared to the video diffusion distance base. You can have the data matrix number, and also in the different steps you can see this is just a one unit, but the diffusion base model need around more than 200 times much lower. So I think this kind of approach also have a very promising in the several future model. So based on that technique, I also have some proposal to extend it to the other modality. Like we have the image. Now I want to adapt it with a new other modality like suppose that we have to describe the post person like this person. At the back side, this is we call this body to this person, and this is style image. So all this task given the input in the style image, vertical appearance, and suppose we want the model need to produce the output, not have this pose, but have the same appearance like this person. That's it. You understand the task? So compared to the existing method, just when I check the state-of-the-art model based on the diffusions, and when I check the need around 1,000 steps to generate one image, the need around 1 minute 60 seconds, and the work on the pixel space is very complex, of course. And this say approach, they only use the pair the image and post pair, and it make it less flexibility during training. So I propose to use one model so that it can was design of the Mask Generative Transformer, and because we can use the parallel encoding, so that you can convert pictures only around 10 steps with the faster generation, which takes around just 1 second per image. And our model work on the mostly change on the latent space. And in the first phase, because first phase we don't need to use anything on the image post pair, so that the first phase is independent from the post. So we can change our image, that we can leverage the pre-trained model for the very large scale image net, for example, in a data set. I'm working on the different data set. We already have around 50,000 images, so it's very limited training data. So by our approach, we can use the pre-trained model from image net and unique language, and we can use that for transfer learning. Yeah, this is some one architecture I propose so that we can recently start using the Mask Generative model. Even we have input, image, and post. We also have the target image. So all of them we embed with some embedding network. And for image, we can use the visible. Visible here, it means we can use the pre-trained mask it. With mask it, we can free this or fine tuning, and we can go to the several self-attention and cross-attention with the style matching module and post-matching for cross-attention here. After training each block, you can have the final output, and this is how the final target we want to put it. In this target, we will mask several positions like this one, 1, 2, 3, 4, and our model will be masked for mask token here. After finish the frame implementation, I try to change the model with around 100,000 steps, and here is some output. Our model can, the left hand side, I try to reduce the papers given the stupid circles, and I try to predict, and they have the output like this. And the right hand side is our model. This is our output here. You can see it can generate some kind of meaningful pose, and not very perfect because we need to train very long time more. Yeah, for some principles. Generative AI is actually very interesting areas, but they require many time to train. And in our current resource, for example, I have 4 GPU A600, A6000. It took around maybe 10 days. Usually it's around 500 hours. And to make many other application study, it took around several days more. So time is so cheap. Okay, thank you. I think it's the end of my presentation. If you have any question, feel free to ask.
Okay, if you have any questions, please feel free to throw the question, and those in the line, please turn off the mic and ask the question.
Can I ask one question about the size of the model that you use for the number of parameters of the model that you use for training your paper?
Yeah, so model I base mostly based on the Mask model, right? For example, here they have the parameter around 200 parameter, median parameter. So our model, we can add several other self-attention and cross-attention. So it expects around 200 more million parameters. So totally we have around 500 million parameters.
Wow, I see.
Any other questions? You can ask any question regarding this.
It's really a great presentation. So I think that everything is very clear, and it's very good that you volunteer for the first presentation. Hopefully that people will ask more questions and try to study this topic.
Yes. With a picture or with my picture. Where here you can ask this one.
So for the reason,
Yeah, picture.
how can you train up like you do the VGN?
This one? I.
You retrain?
Yes, this one I vision bird. Vision bird it means I use a mask retrain transformer. This one I will just transformer from mask model here. Mask it, right? So they have 2 models. So the first step is the first model is the VQN. We have the think of unit architecture, right? So the second model they have is the bidirectional transformer. So in the I prefer vision merge in this model. I try to use this model and chain and try to use this one.
So they provide for you for two resolutions.
Yes, I provide everything, both the 2 resolutions, so that when I train the 2 instructions, I can input the for training.
So in order to finish that training, we have to split it into 2 steps.
Right.
The first step you have to train the unit.
Tokenize, yeah.
Unit we have to train
Only once.
Only one time.
Yeah.
And use that for the next step.
Yeah.
Oh.
So we only do some parameter tuning on the second step. So we need to think of. So here I only main architecture only work on the negative space in the token. Token here is just some integer number. only totally the number, city by city.
So, one question about the trend for your research approach right now in the literature. What is the trend for your research approach in literature?
I usually trend is try to combine with the new condition so that they can generate with some controllability. For example, there is some text, they will put some new requirement into the text, or maybe later they can use some other modality like some sound or something to generate the image as they want.
How about the computational cost? Do they focus on reduce the computational cost of generated shorter time step, like for one time step, or do they focus on the reduce the model size?
I think maybe not because the transformer model is already compact enough, so I think maybe not. This one,
how many blocks that you use for your model?
I think this one we need to do some average study to see what is the optimal number.
So because I think this one, I think the number of blocks that relate to some refinements.
Yeah.
Is it a refinement?
Yeah, no, right. Sometimes we try to make it so that we have some kind of cascade. Yeah, cascade so that you can define and you can get better performance. So we split out. So we try to find the optimal number. Of course, if we try to increase the number, so the model parameter will increase. So it will be slower. So we need to do some straight off. Any question?
I think there is no question more, so we can stop the presentation. Thank you for your presentation.
So this is the end, so you can leave.
Hay quá anh, present hay quá. Chơi vâng nhỉ? Dễ hiểu, quá tuyệt vời. Chứ ngoài nó luôn cà phê thì không được.
심각한 표정으로